Welcoming is an universal quality which gives a smile on face, love in heart, and thoughts in mind. Now I call upon Ms. Jovita, final year, to welcome the marvelous gathering.
Jovita,
Jovita,
kindly turn on your
kindly turn
mic.
on your mic.
A cheerful morning to one and all gathered here for this wonderful Alumni webinar series 2020, organized by Department of ECE, KS Rangasamy College of Technology. I happily invite our founder chairman, Lion, Dr. KS Rangasamy MJF, our vice chairman, Mr. R. Srinivasan, and Dr. K. Tyagaraja, Chief Executive Officer, KSR Educational Institutions. I heartily invite our beloved principal, Dr. R. Gopalakrishnan, KS Rangasamy College of Technology. I kindly invite Dr. K.B. Jayanti, our ever supportive head of the department, Electronics and Communication Engineering. And I delightfully invite our guest speaker for today's session, Mr.N.Kalairajah, who is a staff engineer in Alibaba Group of Companies, USA. He is from the 1994 to 1998 batch, which is also the first batch of the oldest department of our college. I cheerfully welcome all the faculty members who made this webinar possible. Last but not least, I happily invite my fellow classmates for this marvelous webinar series. Finally, I heartily invite all the students from various other colleges for this webinar. Once again, on behalf of all the students, I thank all the faculty members for organizing this enlightening webinar series to enrich us during this lockdown crisis. Thank you, everyone.
Thank you, Jovita. A leader is one who supports us, guides us, motivates us, and makes everything a possible one. Now, I heartily invite such a leader, Dr. K.B. Jayanti, Head Department of Electronics and Communication Engineering, to address a wonderful gathering with her motivational words.
The respected principal, Dr. R. Gopalakrishnan, our beloved chief guest, Mr.N.Kalairajah, faculty coordinators of this wonderful alumni webinar series, participants, faculty members, a very pleasant good morning to one and all present here. This alumni webinar series, actually, it was seeded by our principal, Dr. R. Gopalakrishnan, about 10 days back. And today the program is on. We started it actually with a lot of uncertainties, but still, when we see the magnanimity of how this has taken shape, we, on behalf of EC department, place our sincere thanks for seeding this program to our principal. And we started this program initially. The first call was made to Mr.N.Kalairajah, and he readily agreed without another word, because I should place him with great regards, because this is actually around 9 o'clock in the night there in US, but still he accepted very readily for this particular timing. And I place my sincere thanks to Mr. Kalairajah for having accepted our invitation and made this event start grandly. And in the past few days, the faculty coordinators who supported organizing these events were working wonderfully. And this event has taken shape with 10 alumni from our department. And it is so designed that all the morning sessions are from the alumni who are working in top positions in companies, and few of them even own the companies. And the evening event is from the alumni who are working in the government sector. And I could see a great response particular flyer, which was posted only on Saturday, I personally also received some calls regarding this, and there are a lot of responses, which shows that it again establishes the fact that alumni are the pillars of the institution, and I would say proudly, our alumni are the pillars of this department. So with this note, I would once again thank all the faculty coordinators who have and the student members who have made this event a grand start, and I believe this will be taken forward with all your support together for the next 5 days. And all the student members make use of this event, because this is what is going to help you really. You hear it from your own alumni who were there in this department before you, that ECE is the best. There is no doubt about it that we are the best. And you can hear it from your own alumni, and it will be a great support for your future. Thank you. Thank you all for the opportunity given.
Thank you, ma'am, for your inspiring words. Management is doing things right. Leadership is doing right things. Now I graciously invite Dr. R. Gopalakrishnan, Principal, K.S. Rangasamy College of Technology, to felicitate the gathering.
Very good morning, all of you. I hope I'm audible. Let me know if suppose any audio issue. Mr.N.Kalairajah, speaker, and the today's Alumni Web Series chief guest, and also proud alumni and distinguished alumni of 94 to 98 batch from ECE, respected head of the department, our respected line Dr. K. Stangas, Vice Chairman in absentia, faculty members of ECE department and other departments, my dear students from ECE and different institutions, all of you very good morning. Hope all of you staying safe and eagerly waiting for the exams as well, I hope. So as our head of the department, Madam KB Jayanti has mentioned, like a proposal during the heads of the department meeting, and also it was a message to her, why not we'll do a alumni web series by the this particular day from 8th of June. Immediately she responded, and more than that, as she said, in fact today, among any department of K. Rangasamy College of Technology, ECE has come forward and do this wonderful program. Really appreciate department and the department faculty members for making it happen today, so that the kind of the importance given to my words, and the taking it to the next level. That's what important for any department or college department. Coming to next, Mr.N.Kalairajah. I know it is. I was asking her why it is very early. Then she told me, head of the department told me it is 9 to 10 at US. Then immediately I said, no, okay, go ahead. So thanks, Mr. Kalairajah, for accepting our invite. More than that, evening for you. So thank you very much. Finally, I wanted to mention this thing in very particularly. So all the alumni who will be supporting us, who are going to support us for this particular event, not only for this, and a regular support, that is very important. Thanks very much for that. Very particularly, why this generally people come to campus, or they will be addressing it happening normally, but apart from that, why alumni? What's speciality or uniqueness in alumni? Alumni, it's their alma mater. You guys know they're juniors, so I'll tell you, a little bit extra soft corner would be there. You as their brothers or sisters, their own people. So there will be a soft corner, so that you will extra benefit. They will act as a mentor, so that will play a vital role. So I'll tell you, this alumni web series will going to play a difference in our life for sure. with this, the department for making it happen soon, and also for the initiative. Once again, welcome to Kalairajah for this occasion, being a chief guest for inaugural function web series for the next week. So thank you very much, Raja. Hope you are safe and actually coming to our Islamic College of Technology. Thank you. Good day. Also, thank you. Over to MC.
Thank you for your ambitious work. Optimism is a magnet of happiness, which makes the people surrounded by positive thoughts, good and good people. Now I call upon Ms. Anna Failure to introduce the man of desire and wit. Our most valid guest, Mr.N.Kalairajah, staff engineer, Alibaba Group, USA.
Good morning, everyone. Mr.N.Kalairajah had been in semiconductor industry for more than 2 years, specializing in microprocessor verification. He is currently working at Alibaba Group in Sunnyvale, California. Before this, Bharat Imagination Technologies, Samsung, among on the academic, he has graduated with MS in electrical engineering, telecommunication specialization, and MS in computer engineering, both from the University of Texas in San Francisco Bay Area with his family. We feel happy to invite you, sir, for this webinar. Thank you.
Thank you, Anusha. Champions are the Thank you, Anusha. Champions are the people who are always prepared to depend, ready to repeat, believe in themselves, and dedicated in work. Now, I cheerfully invite such a person who has accomplished success, Mr. N. Kalairajah, staff engineer, Alibaba Group, our most valued guest, knowledge the gathering with his enlightening words.
Thank you all. Can you hear me?
Yes, sir.
Yes, can you hear me?
Yes, Kalai, you are.
Thank you. Thank you all, and good morning. It's wonderful thing to see or hear most of you on the web, and thanks for taking your time coming and attending online, even if it is early. First, let me thank Madam Jayanti. She reached out to me and asked me like whether I can do it. It was really surprising. Contacted her at a community probably a year or two ago, and we hadn't had any mail contact even for the last 2 years. And she said, we are trying to arrange an webinar and want to see if I would be available. I said, what topic? She said, anything that you're interested in. I said, okay, it's fine, because it also gives me an opportunity to talk to students. And thanks to the principal to attending online. I'm going to talk on. It's going to be very general. I'm going to talk because I've been in the what Anusha said. I've been in the industry for 15 years, and I've been in the semiconductor industry. I have not gone into anything else. So my focus is going to be more about semiconductors, what it is, where it is right now, and how it is headed. And since even in semiconductor is a very vast field, and I have specialized more in verification, and even in that, it's microprocessor verification. So I touch a bit upon what I have done and what that are going in microprocessor verification. And after that, probably I'll give you a couple of suggestions for you to use it for your career path advancement. So let me share my screen. Can you see my screen?
No, sir.
No, sir. Can you see it now?
No, sir.
now? Can you see my screen now?
No, sir.
It says it's sharing. What about now?
No, sir. I could not see the presentation. Possibly you could share it on our team so that we will be able to make
No, you don't even see my desktop.
No, we could not see. Probably some network issue, I believe. Even the video also got stuck. If you could refresh, it would be good.
Let me check. Okay. But in start. But at least it's audible.
You are audible, but I think the video got stuck. I don't know about how others, but
Okay.
video I could not. Only the page, you had to get resumed.
Let me refresh it.
Yes. Now we made refresh.
Can you hear me now? Hello.
Yeah, yes, Kalam.
Can you hear me now? What about my sharing? Can you see it?
No, not it.
Okay. So can you send me an email address where I can share my this thing?
Send to jayantikb@gmail.com.
Okay. Madam, I have shared it with you. Let me know when you get it.
Okay, sir. I will check
In the
with madam.
okay. In the meantime, let me go with whatever. So my first slide was more about this, right? So where is semiconductors? Right now, we are going through. We are just having a problem with the communication, and either I'm presenting and you're not seeing it, or somewhere, right? So let's see. 20 years ago, we didn't even have this technology. Now we have come to this level. But where is the problem? So right now in the same example, whatever we are going through, where is the problem? And where is semiconductors involved? First, the path is I'm starting to talk. So my voice, which is an analog one, is getting converted into something digital that the computer or the laptop understands. And what is involved in that? The mic is involved. And then you also have something called as an audio processor. So that actually takes care in a lot of other technologies, which is more like your modem communication, your analog to digital technologies. And apart from it, it also puts in a lot of algorithms to make sure that it is optimized, whatever is sent out is optimized. So there you have your semiconductors. And after that, that should kind of interact with what your actual Wi-Fi, your laptop uses. So your laptop has a lot of other processors, and it has a lot of network network components, a lot of semiconductors involved in that. After that, this has to be transmitted to your local Wi-Fi through a local network. So it might be through Wi-Fi or through your LAN cable. So if it is Wi-Fi, then your Wi-Fi chip is involved, and on the other side, your modems, your router's Wi-Fi chip is involved. And if it is a network, so it has to go through a network interconnect cable, interconnect card, and it has to go through all the protocols, transfer it, and then put it over the wire. And on the other side, it has to receive it, understand the packet. And after it understands, the next thing is it has to transmit it to your modem. From your router, it has to transmit to your modem. So there your communication is involved. It might be cable, and both ends, they have their own processors or chips, whatever is involved. After that, that has to get transmitted to the data center, to your ISP. And in the data center, it goes through, once again, a rack of servers, rack of cards, which analyzes what traffic is coming, what is happening, what is in the packet, and how it has to be serviced and where it has to be routed. So if you see all these things, the problem can be anywhere. And now all these things are possible mostly because of semiconductors. From the start, you have at my end, at the laptop end, you have the chip, the audio processor chip, and then you have your laptop, your processor and other network components on the laptop or on the PC. Then you have components in your Wi-Fi. And after that, you have components in your modem, router, and then your ISP everywhere. So all these things are possible only because everything. So if I'm talking here, you can hear it there or see my presentation. It would happen only if everything is smooth enough. And it can be any problem, because there might be an issue with what I'm saying is not getting converted properly. Then there might be an audio problem. If the video is not coming through, then that might be the video processor is not having enough bandwidth. There is a lot of cache and memory issues involved. So everything is becoming semiconductors right now. And when you see from the top, you see, okay, this application is not running. It might not be the actual application, but it might be the application and the underlying hardware that has to work properly. So only if this coordination is there, then your end-to-end communication or everything happens. In the meantime, can I check with Madam if she has got the... Let me give access.
Yes, sir. Madam got the mail. I am sharing the.
Yeah. Okay. I have given access to the files, so let me know.
Can you give your request to Raghuvaran also, sir?
I just gave it.
Yes, sir. I received, sir. Just a minute, sir.
Okay. Okay. That sounds good. Thank you. So can you go to the next slide, please? Yeah. So this is what I was actually talking about over the last few minutes. Yeah. One more. Yeah. Okay. So if you see the left-hand side is the Wi-Fi, and then you have on the laptop, you have the semiconductors. It's basically your audio or a camera. And then you have the processors involved to convert that analog stream of information to digital. And then next is the Wi-Fi in the connectivity. And it might be Wi-Fi or anything related to your network. So there you have your Wi-Fi chip, your NIC. And after that, you have your modem. And in the modem, you also have your power chip because it has to take a lot of power related issues into account. And then it goes into the data center where you have your high-speed switching chips, and then you have a lot of acceleration chips and everything. So if you see this technology, these have evolved only in the last 10 to 15 years. Before that, let me give an example. I'm from the 94 to 98 batch. At that point, laptop was a luxury. We didn't even have Wi-Fi. And I would say none of the data centers, whatever we have right now, it's like huge. If I compare that data center to what we had sometime probably in 94, 95 in that time frame, probably it's 1 by 10,000 times of that. So we have evolved a lot. If we go to the next slide, I'll just show you what has come. Yeah. So if you this slide actually tells about how the semiconductors have evolved over time. If you see it, most of these stuff, if you go to the right bottom corner, so that is where most of the evolution has happened, and that is what is pushing the semiconductors to the next level. If you see, it starts with the mobile phone in around like 98, and after that, you have the smartphones, which actually revolutionized a lot, because if it is mobile phones, it was mostly only the communication that was involved. But now with smartphones, there's a lot. It's a different paradigm, because you need to have, you're just kind of carrying a whole computer in your hand. And if you want to have a computer in your hand, what has to happen? It has to communicate properly. It has to show the videos. It's just not the audio communication that a regular mobile phone has. It has to have a lot of other things. And now on top of that, you have the app and a lot of software. So your hardware has to handle everything in that. So now it is, if you run your hardware, if you run your software, your hardware should be capable enough to handle that. And that is the only way you can make sure that your software, whatever software you write, is going to work as required. So that is where your smartphone is evolving. And then after that, you have your wireless communications. So these are the things that are pushing the semiconductors to the next level. And second thing is, even if you had a computer, compare it with a laptop. Your laptop or your desktop, right, will have kind of the same functionality as that of a smartphone. But your smartphone has to be more power aware. it should consume less power, because you cannot have the same amount of power that a laptop or a desktop consumes. So that is one more area where your semiconductors have to improve. And that is where, when the processors were developed with a process node like 180 or 130 nanometer, they said the power consumption is high and we cannot use those things very efficiently in smartphones or any of the handheld devices. So we have to go to an advanced node, because if you see semiconductors, there are three main factors that actually drive things. It's a power, performance, and area. You can have the same functionality in different chips. Like you can have the same processor within a mobile, within a laptop, and within a desktop. But the area that the processor occupies within a mobile phone should be comparatively less compared to the one on the other two. And similarly, if you see the performance on a desktop would be more higher. So you need a higher performance processor in the desktop side compared to your mobile phone. And power, your mobile phone should be consuming less power, but your desktop, mostly because it is always connected to a AC outlet, it would it's not much concerned about the power issues. So these were the things that are driving your semiconductors to the next level. So instead of 130 or a 65 nanometer, now we have come down to almost like 10 and 14 nanometer. And there is a lot of experimentation and challenges going on with 7 nanometer and 5 nanometer. So can you just go to the next one? Okay. So if you see this is from one of the recent reports that say where your semiconductor industry is going. And if you see on the left side, it mostly the data processing, which data processing in the sense like these are the devices that are involved in getting the data, analyzing it, and then distributing or processing it. So these might be any of the servers that you see in the data centers, or these might be anything where your AI or machine learning or anything is happening. And then your communication electronics, where your modem, your Wi-Fi, or your network, anything related to networking is another big area. And these two had been there for quite some time, but they've evolved very significantly over the last 10 to 15 years. And if you see in that, the last two, right, consumer electronics and automotive electronics, those are very new fields. If you had looked into a car or any vehicle probably like 15 years ago, you can count the number of electronic devices inside that vehicle on the fingers of your hand. But now it has changed dramatically. I have one more slide where I can show you what are the different things that go into automotive electronics. And so that is one field that is actually revolutionizing the semiconductor industry. And consumer electronics. So consumer electronics can be anything, like, say, for example, your smart speaker or your cameras, your audio, video technologies, anything. So right now, these are now you have lot more of data that needs to be processed and processed effectively and optimized, and then they have to be sent out. So this is where a lot of revolution and a lot of evolution is coming on. And if you see on the right-hand side, this is basically the pyramid, if you can see. So on the top level is what all your applications are. It can be a lot of different things, your machine learning, mobile, or anything, whatever you see. And below that is how they actually get interacted with the hardware. And so if you see the hardware, most of the things is like what they have said, is split up across different 4 different areas. One is the IC design. So when I say IC design, it is more about what is the architecture involved? How do you design it? How do you code it? How do you make sure it is working fine? And then you give it out. And that is one part of what a product is. The next one is the wafer process. And wafer process is not a simple thing. This is where your whole chip gets converted. Whatever you write in your software, whatever you're verified, whatever you're designed, is actually made into using actual silicon, and you see the actual chip. So this is where your wafer process comes in. And then memory is another part. And right now, memory is another big chunk of industry or important ingredient of any product that comes out, because especially now with machine learning, AI, and all of these new areas coming, there's a lot of data that have to be analyzed, that have to be stored, that have to be processed. So memory is another major area. And IC packaging. So whatever comes out of the wafer process is more like a chip. So that's more used for testing purposes or prototyping purposes. But you cannot use directly on a semiconductor or end user product. So you need to identify what is a heat sink, what is a pin count that is required, what is the power, and how does it fit on the motherboard, how does it fit with the whole system. So that's another major area that is involved. So there's a lot of changes and a lot of things, a lot of changes and a lot of new ideas that are going on in all these areas. And these are majorly driven by one of the top level end applications. So basically, let's take an example of machine learning, right? So if you take machine learning, you need a lot of data. You need to analyze those data. You need to process it, and then you have to give out the results. So you need faster. If you take a look at it, you need a lot amount of memory to store that data. And that memory can be, I'm just not saying it's a particular type of memory. It can be a hard disk, it can be a cache within your processor, it can be your memory in the system, it can be anything. Memory is a hierarchy, a lot of levels of hierarchy. So these things have to be optimized, these things have to be fast enough. And the other thing is, when you get into machine learning, you have a lot of processing that's involved. So you need your bandwidth, you need a good amount of network that's involved. And your processor should be able to get that faster, analyze it, work on it, calculate it, and then give the results. So your processor has to be fast. Your processor should not consume a lot of power. And now with machine learning, you have so many processors. It's just not a single processor that does it. It has, they call it a sea of processors. So everything, you have a lot of processors. So your power has to be less. Your processing power has to be high. So now all these have to be accommodated in your underlying software hardware. So these are the things that are asking us in the industry to see what can be done and what can we make sure that we achieve whatever we require. Can we get to the next one? Okay. So if this is more like follow up to the earlier slide. If you see, till now it has been more about the mobile world that has been driving the industrial semiconductor revolution. But the next one is going to be AI and 5G. And if you look at it, if you look at AI, it's more about processing. And if you look at 5G, it is more about network and speed. So these are the two major areas that is going to help you or going to push semiconductor to the next level. And anything that is you call as robotics or automotive or anything is part of these things, I would say, because if you look at the end application might be a bit different, but the underlying one, if you put it under the big umbrella, it's going to be either AI or 5G that is making it sure that, okay, we can achieve things, whatever is required. Can we go to the next one? Okay. So when I say AI, this is a typical how a data center looks like, because once again, AI, you have machines that do a processing, that might be end user machine, and finally it might go into the data center, and there it does a lot of more processing, and then inference, and then learning, and then finally gives us a result. So if you see in this slide, you have a lot of things that are semiconductor driven. If you look at the local IT, let's start with the LAN IT. So that has a lot of semiconductor, which is mostly related to networking. And that would have to be optimized for how the data center is set up. Next is your WAN. So WAN has to be sure, has to have the ability to get information properly from all the networking edges, and then process it, and then give it to the data center. And then you have the server. So server, if you see, it has to have a lot of processing power. It should be optimized for power, optimized for area, because you're going to use a lot more processors and a lot more memory, your hard disk, whatever it is. And these have to be optimized. And then you have your storage. So everything is now semiconductor driven. So earlier, if you probably 15 or 20 years ago, you wouldn't, having one server was a huge thing. Now a server, nobody calls it one server. It's a huge farm of servers. That is what we have nowadays. And even with that, it becomes very difficult to process and get information right. So one example I would like to give is, right now there are a lot of companies, a lot of research institutions that are trying to use these huge farms, the huge farm of servers, to calculate or to find the vaccine for COVID. And think about it. So they have to go around with a lot of information from a lot of data sets to analyze it, identify, and then get to a conclusion. And it's not a simple thing, because the amount of information that is available is huge. Now you need to actually go through that information, sort it out, and then try to come up with a with a solution for a vaccine. So now you need a lot of hard disk or hard storage area. This was unprecedented a few years ago. Now it is like a common thing, and these are given to like supercomputer farms, where they could analyze and get the result. So these cannot be done within a simple one-stop area. This has to be done at a huge level, and that is where your requirements for your semiconductors make a lot of change. The better your processor, the better your networking, the faster your memory, the faster your networking equipment, the faster your processor is, you might be able to calculate and analyze and give the results faster, or else it's going to delay. So these are the things, these are the fine nuances that have to be taken into account. And these are the things that are pushing semiconductors to the next level. Next slide. So this is one area I would like to, one slide where I want to emphasize on different companies that are just working on the AI landscape. So if you see on the left, most of these companies had been just pure software companies like Google, Microsoft, Facebook, Amazon, or Apple or something. But now they are using, now they have been trying to, they have been getting hardware from outside, and they have been porting their software or using the software to run on that hardware. The problem is these hardwares, whatever they were getting from outside, were not customized. They were more like a general off-the-shelf hardware. So those were not developed with AI or machine learning or any of these things in mind. So your power, area, performance, everything would have an effect. And now, if you want to run a software and want to have it with a better performance, your software and your software should understand your hardware. And that is where a lot of these companies are trying to develop their own hardware. And especially if you see Google with your tensor processing unit or TPU, they did something totally new in the industry, because they came out with something that is not a GPU, that is not a CPU, but something a processing unit. And it worked well for them, because the way they designed it, they said, okay, I don't care about anything else. I want to make sure that whatever my software or my application does works fine, and I want the highest throughput. So they designed the hardware with their software in mind. So that is where most of these software companies are investing into semiconductors. And the next is the traditional companies, which have been doing semiconductors for quite some time, like Intel, Samsung, and NVIDIA, or AMD. And they now, because of the emphasis and the necessity from software side, they are fine-tuning their semiconductors, and they are trying to come up with more modifications to whatever they have. And now the startups are another big one, because if the problem with all these big companies, traditional companies, is whatever they develop, they don't develop with a very niche area. They want to develop something that could be used on a large variety of applications. So in that case, for them to fine-tune the architecture and change the architecture, it becomes difficult. So that is where most of these startups come into picture. And these startups come with totally different architectures, totally different ways of how to analyze things, how to implement things. And these are some of the revolutionizing ideas we have seen in semiconductors over the last few years. And then on the right side, you have a lot of IPs, because when you see a system nowadays, it is just not a single processor. It has a lot of other components. And these are some of the major companies, design services. They provide IPs, and these IPs, some of these IPs are not like a bottleneck in your overall data flow. So they can be used off the shelf, and they provide a lot of advantage by using them. Next slide, please. Okay, this is what I was telling you about the automotive electronics, right? So 15, 20 years ago, you wouldn't have these much of electronics. Now, everything, apart from the body and probably the engine in the traditional vehicles, everything else is having at least one or the other semiconductor part. So braking is one major area, automated braking is one major area, cruise control is another area. Then you have the ADAS, which is your automatic detection and analysis. So that is another area. Navigation system is one, security is another. So these are major things that are coming up, and these are something really new. Over the last 5-10 years, these have evolved from nothing to a huge industry. So now there's a lot of information that has to be processed, analyzed, and then given to the control of the car or to the data center, wherever it is, to make sure that the vehicle is on a proper route and it goes properly. So that is where, obviously, manually calculating and analyzing that is out of question. So you need some sort of a semiconductor, some sort of a processor or a hardware that would do all these things and give the information. So that is where your automotive electronics is one major big umbrella that is pushing semiconductors to the next level. Next one. So another example is from the big cars to the smaller ones, right? So if you see the there's an example of an Apple Watch. If you see it, you from an outside you just see it as a watch, but what are the different things where semiconductor has an impact? If you see from the top, your touch screen is kind of a sensor, way of sensor. So there your semiconductors is involved because your screen should be good enough to understand your touch. And then your display module, whatever you want to display out, like whatever is on the screen. So that is your display module. So that is also semiconductors. Then your NFC antenna, your near field communication, your antenna should be good enough to get your signals and then transmit data. Then your speakers should be good enough. So once again, your semiconductors is involved. Battery is another major area where semiconductors is involved because your battery should be good enough and it should not be too high to burn the watch or or burst it. So battery is one another thing. Then you have the interconnect PCBs to make sure that your connection to the motherboard and everything is fine. There is no cross signal and all those things. So those have to be taken care. Then your wireless charging. So that is one another area of semiconductors. Your sensors and your antenna, WLAN antenna. So these are a lot of things where you have a lot of analog related semiconductors. If you see in this, your touch screen, your speakers, your optical pulse sensor, your your WLAN antenna, all these things have a lot of analog parts. That is, so nowadays, if you see semiconductors and especially with IoT and AI, analogs are having a comeback. Earlier, it used to be like probably in early 2000s, it used to be only a digital world. Mostly people were going into the digital world and analog was not that much. Now, with IoTs and AI, people want to get information from outside and then process it. So to get that information, you need that analog to digital conversion. And that is where all these analog sensor-based things are getting a big highlight. Next one. Yeah. So now in the earlier one, what we saw was we had all these analog stuff that were just interacting with the outer world, like your human touch or your eyes, your vision, your pulse and everything. But inside it, all these analog have to be converted into digital so that the computer or the processor understands and then transmit it to them, analyze it. And if you take a look at it, for a simple Apple Watch, I think this is a couple of earlier iterations. This is not the latest one. A simple Apple Watch itself has so many processors and so many underlying semiconductor parts. If you take at the left top, you have the Wi-Fi. So you need to have a chip that would analyze the Wi-Fi. And then the LNA, once again, a part of the Wi-Fi. Then if you come to the power dialog, the power management unit, you need to have a good power management unit that would make sure that your power is distributed properly, it works, and your whole watch works properly. Then you have the controller, ADA touch controller, because it has to get the sensor input from your touch sensor has to get converted, and that has to be understood by the software. So that is where your touch controller comes in. Then your audio codec is there to make sure that your audio is converted properly into the digital format. Then your signal booster, on the right, and the major thing is basically the memory and the actual processor itself. But apart from it's just not one processor. What I'm trying to say is, even within this simple watch, whatever you buy, you have so much of hardware that is integrated and present. And see the complexity involved. So earlier, like a few years ago, you wouldn't even have an idea that okay, these were the different things that would come into a watch. No, you didn't even have. But now these are like a very common thing. A watch, when you say okay, you're going to design a watch. So these are the different things. These are different components, semiconductor and hardware components, that you think, okay, these are things that these should be present inside a watch, and without these, I cannot have a smartwatch. So this is where the industry has come over the last few years. Next slide. So from watch, let me get to an example of what AI processor would look like. So in your computer architecture or your microprocessor, I don't know what you guys are learning right now, because when we learned, we had microprocessors like 8085 and 8088. And recently I see a lot of at least the basic computer architecture books having RISC-V or a MIPS processor or anything like that. But those are good for understanding. But at the industry, now you don't use a single processor, at least with AI and machine learning coming in. These have, like what I was telling, these have gone big into farms of servers. So if you look at one server or one chip, what does it look like? So if you look into this picture, right, into this, so you have so many. So this is from a recent NVIDIA chip. If you see at the, so this SM is called as a stream, I think it's a stream processing machine or something like that. So streaming machine. If you look at it, it has 4 different areas, and each area has floating point core, 7 floating point cores. Then it has a tensor core, it has an integer core. If you look at what you have been studying or what are in the textbooks, you look at a single core, and you have 7 or 8 of those within one of this squares. Now you have 4 such squares. So think about it. It's like 32 or 64 out of 64 times of what you're studying, right? So that is a simple stream machine. But even this is not enough. Can you go to the next one? No, I think there is one more. Didn't come back. Yeah. So now we were seeing a stream machine, right? Now, if you look closely into this, there are like 6 big boxes. And within each of these 6 big boxes, you have 2 rows. And within these 2 rows, you have another 7 small boxes. So each of these 7 small boxes is a stream machine that we saw in the earlier slide. So think about it. So the smaller stream machine had around like 64 cores, 64 different integer or floating point cores, whatever you want to put it. Now that multiplied by 2 and that multiplied by 6 is what a full GPU is. And apart from it, if you also take a look at the sides, you have the memory controllers, and then in the middle is a big cache. Cache is one more thing, one more type of a memory, which is a faster memory, mostly integrated inside the processor or very near to the processor. So earlier, you wouldn't even have so much cores, you wouldn't even have so much of L3 cache or memory inside your system. But now these are some things that are required for processing the huge amount of data that we have. And this is where things are getting a lot of the semiconductor industry and everything is more complex, because even developing a single core within that stream processing unit takes a lot of time. When I say time, it is from design to from the architecture spec to the architecture to the design implementation, then making sure that everything is properly done, verification, then going into the back end where your power, your timing, a lot of other things are analyzed, and then it comes out. So even to get one core to work, it's a huge deal. Now, if you have so many cores, trying to make them work in unison is very difficult. It's a mind-boggling process. So if you think, okay, hardware is nothing, no. Hardware is, there are a lot of things that are involved in hardware, and only if you make sure that your hardware is good enough, then your software would work. Next slide. Okay, so that one thing, whatever you are seeing, right? So that is that's one of the largest GPUs that is available out in the market. So that is the one that on the right side. Now, Cerebras is a recent AI-based startup. They came out with a chip. So think about it. The right side had so many processors, so many transistors and everything. Now, compare it with Cerebras. So now that large GPU is something very small. Can you go to the next slide? So this is what a Cerebras chip looks like. It's like around like 46,000 square millimeter, which is like 8.5 inch into 8.5 inch. Think about the number of cores, right? It's like 400,000 cores on a chip. And your software should be able to run on it, utilize it properly. And that's a requirement. Your software is so complex. That is why you need so much of a hardware. Think about the SRAM chip, SRAM 18,000, and the interconnect speed. It's not gigabits, it's petabits. So that is where your networking is evolving, and a lot of. So this is where semiconductor is going. Probably that even this chip is going to be seen as something that is small. That'll be much more bigger chips that would be developed. Can we go to the next slide? In the meantime, I just want to understand how much time we have.
We have another 30 minutes to go, Kalai, including
Okay.
the discussion session.
Okay, sure. Okay. I'll try one. Okay, thanks. So if you look at the semiconductor, right? So trying to get a chip from spec to the final chip and get it running properly, there's a lot of things that are involved. So this is one SoC. SoC is a semiconductor on chip. Now system on chip. So earlier you just had a chip. Now it is a system. When I say system, anything. If you go to the earlier slide that I showed you, the Apple Watch slide. So that board where you had a lot of processors, that is a system because it does a lot of different things. So that is where it is going. So trying to develop one of those SoCs, it involves a lot of steps. So on the left side is where your hardware blocks or generic hardware blocks are. These are mostly like IPs you get from IP in the sense of intellectual property things that you get from other companies. If you remember the AI slide that I showed you, on the right side, there were a lot of companies like ARM or Cadence or Synopsys. So these would be providing one of their chips directly, and you can use it with very little configuration. So these are general hardware IP blocks. So, and then on the top is the specification of the chip. So this actually tells, okay, if I'm going to develop a chip, what are the things that I need in the chip? Okay, how many processors? What is going to be my final application for the chip? Who is going to use it? What is going to be the power consumption, or what is going to be the application that is going to run on? How fast should it run? And what are the performance benchmarks I should meet? So all these things would be taken into account, and that is where you specify what your hardware components you need. Then you have your architecture platform, and then there, if you see on the left side, you have the application specific hardware IP blocks. So there are few blocks, like say, for example, nowadays, security is one major concern in chip design. And creating a crypto or a secure based processor is a challenge. And trying to get, so because crypto itself involves a lot of processing, and you don't want to develop something that is uh, that involves a lot of it's kind of error prone, because there's a lot of math involved in designing a crypto processor. So there are companies that do, or even probably in-house teams that do very specific things that are uh, do things that are very specific to a crypto engine. So these are some specific application specific IP blocks that are getting developed, because you want to offload more of the work from the main processor. And then all these things you integrate, and then on the top is more of the integration. And then once you integrate everything put together, you developed a simulation environment. And this is where you functionally simulate. When I say functionally simulate, is you run your stimulus, especially I don't, when it's a stimulus, you don't, at least from the hardware side, you don't run a full application, because that becomes very difficult. So you kind of develop your stimulus with your at the hardware level, in the sense like, okay, I want to toggle this pin, I want to drive a tick on this interface, I want to simulate something like, okay,
ஈவினிங் செஷன் எப்போன்னு பார்க்க போனேன், அப்புறம் தொட்ட
I'm,
வர மாட்டேங்குது எப்படி.
I'm reading from the I'm reading from the memory, and then I'm writing it to a memory, and in the meantime there is some other traffic coming from a different node from a network, from another part of the network. So I want to generate all these scenarios at the pin level. So that is where your functional simulation is involved. And then after that, so if you remember the earlier slides where I showed you the NVIDIA GPU or the Cerebras system. So when I say 40,000 cores, 400,000 cores, that you don't verify each and every core. You verify one core or probably a set of cores, because verifying or trying to test, make sure that every 400,000 cores is working fine, is very difficult in a hardware environment. So that is where you go to the next level, where you have the emulation, which is like kind of abstracting out your hardware and then running it fast. So that is where your emulation comes in. And after that, you also have the physical design, where they go into the finer details of how your transistors are implemented, or if you have a mux or your flip-flop, how is it actually implemented, can we optimize things. And they look at timing and design check rules. A lot of that's a big area where you need to actually go deep into the actual implementation of how your chip is done, or parts of the chip is done. And then you go into the prototype and all, and your specific application prototype. So why do we do all these things? The problem is replacing a hardware once it is out into the industry kills the company. Meaning, like, it is very difficult to replace a hardware once it is out into the market. So that is where you have to put in so much of efforts to make sure that your hardware is right. And if you typically look at designing any of the processors, any of the hardware, like, so if it's a simple chip like a Wi-Fi or a networking chip, probably anywhere from 6 to 9 months is what is taken. But if you look at processors, it takes anywhere from 1.5 to 3 years, or sometimes even 6 or 7 years. So that's a very, very challenging one to develop a processor or any hardware, especially at the SoC level. It becomes even more challenging, because you need the application, you need the full prototype and everything. You need the specific implementations of each and every parts in your system. So it becomes very challenging to implement SoCs. Next one. So that's the typical SOC flow. But if you break down the SOC flow, let me go a bit fast into the slide. So the IC design is one thing that would be important to look at when you're designing one of those 400,000 cores within the Cerebrus chip, or a single core within NVIDIA system that I showed you. So even for that, you need to understand the design. You need to you need to implement it using mostly Verilog or VHDL, one of these languages. Then you need to simulate. That is where your functional simulation and everything comes in. Then and your verification comes in. So that is what most of the people call as the front end of a system. And then after that, in this middle column is where you look into, once you verify it, then you create something called as a netlist. And that netlist is what is given to the backend. And that for the backend, it has to go through a lot of validation. It needs to do a timing verification. And then once the netlist is derived, it goes more into the placements, routing, and power related stuff. And once again, timing verification. And you also need to go through the electrical design check rules and everything. So so this is where you're more of the final level of implementation is looked at, more like your transistor level, or your specific very small module like a flip-flop or a mux, or any of these are looked at. So if you look at, there are a lot of opportunities, a lot of challenges involved in each and every level of designing of a chip, of a semiconductor product. So if you think that, okay, I don't see any opportunities, no, there are a lot of opportunities. Only thing is you have to give a try. You have to understand what is going on, and then try to learn more about it. Next slide. Okay, so it's kind of a wrapping up. So careers in hardware. Yes, I think recently, if you remember, a couple of days ago, Sundar Pichai, who's CEO of Google and Alphabet, he was giving an interview and he said, "Hardware is hard. It's really hard." So it is not like software. It is really challenging because you need to understand what is the underlying implementation, and it becomes very tough for a normal person. So I'm saying, if you know hardware, it is easy to go into software. But if you know software, coming back into or getting into hardware, no, forget it. You cannot get into hardware. It is like that. It is challenging because, and it is multifaceted in the sense, like you now, with so much of iterations, so much of changes coming into semiconductor, and you want the product fast into the market, you need to make sure that you verify it, you implement it, you design it very fast. So your traditional approach of doing things in the semiconductor industry has been changing quite a bit, and a lot of software practices are getting implemented. So if you see nowadays, earlier from the back end, there has been not much of tools. Now there are tons of tools, tons of new companies that have come in developing these tools. And in the front end, if you see, similarly, earlier it used to be more like a Verilog or a VHDL or E or Specman based design and verification. But now these were more like a static, like it becomes very difficult to maintain these and get the proper results. So now with people are kind of consolidating on the verification side. Verification is one major area where a lot of emphasis is given in semiconductor. If you see, to get a chip out, you need the design team, and the design team is the one that actually implements. And then this verification team is the one that actually verifies and makes sure that things are fine. And if you see the ratio for a simple design, you might have like simple module, let's say one of the modules in Wi-Fi, probably you have 2 designers, but for verification, you might have like 4 or 5 verification engineers. And now the verification has to be done at different levels. You cannot do everything at the same level. So you have to do something like what they call as the unit level, which is more like a module level. And then you do something at the higher level, which is kind of a full chip level, then at the SoC level. So you need a lot of things that need to be driven from the verification side. And that is where a lot of software changes are coming in. And if you're in verification or design, you're just not going to do code and do things. You are going to write code. If you're in design, well, sometimes you might be writing code. Sometimes you might be talking to the architecture team to understand what it is. Sometimes you might be talking to the verification engineer to solve a problem, or sometimes you might be talking to a backend or a physical design guy to see your closing your timing. So that it's not like a simple job nowadays. It's like multifaceted. Even take a verification engineer. You have to set up your infrastructure for verification. You have to understand the spec. You have to talk to your designer. You have to talk to your architect. There's a lot of things that are involved. So it is how much you need not worry about. Okay, there's not much of learning, but no, there's a lot of learning, especially being one of the if the team is new or if it is a new product. There's a lot of learning involved, especially compared to software. And it is more specialized. Like yes, you might be looking at, say, if you're implementing a DSP chip, you'll know a lot more about DSP. And from a software point of view, okay, this is how it works, but you don't know how the underlying hardware is. But if you're working at the hardware level, you will know the hardware, and you also know how your software would work according to according to your implementation, and what are the different things your software might look at or overlook. So these are things. And one thing to strive and get going in the industry, it's not specifically for hardware, but anything is get out of your comfort zone. Don't be like, okay, I know this, I can survive in this world. No, it's going to change, especially now, given the COVID situation. Okay, whatever you have been taking things for guarantee is not the same. There are a lot of challenges, a lot of things are changing. Similarly, in industry, things keep changing, and you need to get out of your comfort zone, learn something new, and learning should be kind of a daily process. Next. Okay, this is a simple thing. This is nothing related, very specific, nothing specific to semiconductors or anything, but just in general for you to advance. Let's say you have, for anything, you need a goal. Okay, so that is the point. And then to achieve that goal, you need a starting point. Without a starting point, there is nothing. And to achieve that, you need something to put in. So say, for example, if I want to finish a project, I need to understand that project. I need to be committed. I need to implement whatever is done and then see the results, debug it, or something like that. So that is the commitment that is required. And to achieve that, sometimes you don't go in a straight line. You have to go roundabout. You might have failures. You might not get whatever you want, or you have to take a different approach, get something else done to get this result. It's not simple. Nothing is simple. So that is where I have the different arcs. You can go anywhere or in any route to achieve it, right? Next. So if you change your so now what I want to say is the 4 C's, right? So change your starting point into confidence. Without confidence, you cannot start anything. If you say, for example, if you want to ride a motorbike, you can't say, I want to ride a motorbike. You have to have a confidence. So I am going to ride a motorbike. I will do it. So only with that confidence, you can kickstart something. Without that, it's going to be very difficult. Next one. And the goal, whatever you have, right? You should have something, your clarity. Okay, when I'm going to ride a motorbike, okay, I will ride it. I'll ride it safely. So that thought and that clarity should be there. So your confidence should be your starting point, and clarity should be kind of your mission, your vision, whatever you want to do. And this is going to be like for anything, whatever you do it, right? And to achieve that, you need to put in your efforts. So for riding a motorbike, okay, you have to sit on it, you have to balance it, you have to show the balance, you have to put in your effort. So without effort, nothing comes in. So if you want to swim, just get into the swimming pool, dive into it, try it. So that is where you have to put in your commitment. And sometimes the commitment is not a straightforward path. You have to take a reroute, you have to go somewhere else and then come back. So that is where your coordination is. So only if you have all these 4 C's, you can you can achieve success, I would say. So let me give you a simple example, right? Being in the semiconductor industry, and this had been a big learning for me, is Linux. Linux is something that was nowhere probably 20 years ago, 25 years ago. Now Linux is the industry standard for any of the servers, right? Where did it come from? So confidence. So they wanted something where, okay, I want to make sure that people are not reliant on a particular vendor or a particular specific architecture implementation. So they said, okay, I want to go ahead, I want to make sure that software is kind of free and it is easily maintained. People know what is going on inside, and I can do it. So that is the clarity they had. And the confidence, okay, I can build something from scratch. That is where the confidence came in. And the commitment. Think about the amount of efforts they had put in to write so much different software, so implement so much of things on different types of hardware. Now Linux runs on 1,000 different hardwares. So that is the commitment Linux had put in. And coordination. It is not easy. You need to get people with the right mindset, with the right approach, and you also need to build industries, you need to build companies that would actually get you through this phase from your confidence to your goal. So that is where they built a lot of new industries, lot of new applications, and you have to showcase that, okay, Linux can do things. So that is where they had put in a lot of coordination and with different vendors, different industry consortiums and everything. So, and that is where Linux is right now. And that is one way they had achieved it. And I had been in Imagination Technologies, and Imagination Technologies had acquired MIPS a bit earlier. So that is, and that is one more learning that I went. MIPS, if you had gone through computer architecture, MIPS is one of the variants of a RISC processor. It is very simple to implement. It was really good. But they didn't, personally, what I would feel is they missed out on the mobile race. They were really good compared to ARM in the implementation. That is fine. But they had the commitment from the hardware side. But if they want to go into a new industry like the smartphone, it's just not the hardware. You need to build an ecosystem. That is where the coordination I want to say. You need to have the ecosystem to make sure that you have good enough applications, you have good enough vendors who could write applications to run on your hardware, port it to your hardware. If MIPS had it, they would have been a success today. But unfortunately, they didn't concentrate on it. They just thought, okay, I'm good with hardware. No, and that is where ARM right now, they are making big bucks because they were able to understand the ecosystem. They were able to vision and then put in their mind that, okay, it is just not the hardware, it is a lot of software and a lot of coordination involved with other vendors, other people, other players in the market to push their agenda. So think about it. Even if you want to achieve something, it is just not you. It is a lot of ecosystem that has to accept whatever you're doing, and you have to fit into that ecosystem, or else it becomes very difficult. Next one. Yeah. Next. It's almost done. So yeah. So to remember this, so remember can you go back to the earlier slide? Yeah. To remember this, it's like the 4 C's of a diamond, right? You remember this diamond picture? It's a 4 C's. So a diamond is characterized or gets its appreciation with the 4 C's: color, carat, clarity, and cut. Similarly, if you want to be appreciated, you need to have a confidence. You need to put in your commitment to get to your goal, and obviously you need to have the coordination to make sure that whatever you achieve is getting utilized and you are also seen. Okay, thank you. That's all I have. Hope I didn't run over time.
That was a great presentation, Kalai. Over to
Thank you.
MOC.
Thank you, sir, for your enlightening words. Now the platform is open for any queries. Students, if you have any queries, you can ask our guest.
No questions? Everything is clear?
Good evening, sir. I have a
Yeah.
question. Yeah.
Sure.
So, myself Harish from final year EC.
Mm-hmm.
So when you were talking about the largest GPU with trillions of transistors,
Mm-hmm.
you made a comparison, right? So my question is, uh, you also said that it has a lot of data processing speed. It's like its data processing speed is petabytes per second. Like that's the metric in which you mentioned. It's
Mm-hmm.
it's it's data speed. But right now my question is, can we actually build a system where we can efficiently use the GPU to ensure that we are getting 100% output from it? Like let's say if there is a bottleneck between the RAM and the VRAM,
Mm-hmm.
that's the GPU, then we won't
Mm-hmm.
be able to achieve 100% efficiency with the GPU, right? I mean, is my question
Right.
right? Like,
Yeah, go ahead. Yeah.
yeah,
So
yeah. So,
is that your
yeah,
question or you have something else?
yeah. So my question is like, do we have technologies where we can transfer data at such speed to to and fro GPU and the RAM? That's my question.
So yeah. Um, like what I've been saying, right? So there are a lot of new startups that are coming up with. I think there is I don't remember the name of a startup. So this startup, they came up with something called as some memristor or something, and they were using kind of a memory-based resistor, and they said that that could be used for faster processing. I'm not sure. I saw this probably a few months back. I'm not sure what is their current status, but those are something that people are trying, and then companies are trying to come up with. There, so like you say, yeah, that will be certainly a bottleneck, especially with the way your processor speed is there and your memory speed is. Um, few things are happening as they are trying to come up with multi what is it multi-cloud memory access, and that is where your DDR4 generally most of us have a DDR3, and then you have a DDR4, then you have a DDR5 coming up. So these are things that people are using it, and people try to use these things because they don't want to change the full hardware, so they can just change the memory part or the memory controller. But if that would allow you to achieve a better speed, but yes, certainly you will not be able to um, close the gap between the processor and memory. So that is where kind of startups are coming up. They are just going to the drawing board and starting from scratch. They come up with totally different architectures. They try to experiment with different things. Some are a hit and some are a mess, but yeah, that is where a lot of changes are also happening, and especially like with AI and a lot of data available right now, people are
Yes.
experimenting and trying to come up with new things.
Thank you, sir. Thank you for your quick answer. Thank you.
Hello. I have a question. Can I ask?
Sure, madam. You asked me a lot of questions.
Thank you. Actually, we were doing a program in TensorFlow with CNN Kalai. And we were trying to download it into the Raspberry Pi for hardware implementation.
Okay.
Now, my question, and it also worked actually. But now my question is, supposing we do this with the TPU as developed by the Google, right, the Tensor processing unit, what difference it makes when we put it in a Raspberry Pi and when we put it in that TPU?
Okay. So if you look at it, whatever Raspberry Pi is developed, Raspberry Pi is more like a very small processor or processing element, right? TPU is more of a huge chunk or kind of a ghost. So one thing is power. Second thing is Raspberry Pi was developed by a different company, and it's more like, let's say, you want to you want to eat some food, right? If you get it from outside, it's going to be different. But if you cook inside, if you cook it at home or cook within your family, it's going to be different, right? Because you know what your taste is, what your consumption is. Similarly, so whatever Google developed, right, the TPU, it has been developed with their application in mind. So if you're running their TensorFlow or your whatever application, that would know how your hardware is, especially, let's say, it your TensorFlow creates some data structure. That data structure would be kind of optimized for the hardware, for the TPU. So TPU, if you look at any hardware, it has its own caches, it has its own registers and everything. And when you're writing software at the top level, probably it's very difficult for you to customize your software specifically to the hardware. Only if you're a specific vendor, if you're writing for a specific hardware, then it is fine. But if you're writing for a very generalized hardware, it becomes very difficult. So that is where your TPU implementation would give an advantage, because that knows, because the TPU was developed in-house and TensorFlow was developed in-house within Google. So probably they would have collaborated, and then they would have developed TPU, they would have tweaked the TensorFlow according to TPU's implementation. And that is where your performance, your power, everything would be better than running it on a Raspberry.
Okay. I got it.
That is where most of these software companies nowadays, they are trying to build up a big hardware team. Think about Apple. They want to, earlier, if you see Apple, they were having only a processor team, a CPU processor team, and they were getting a lot of IPs or any of the other hardware from outside. But now, if you see, hardware is a big thing in Apple, and they are having their in-house processing, in-house design teams. Because one thing for a company like Apple is they know their end product is going to be something that is run through a Apple iOS or one of their smart OS, one of those their OS. So they know what their software is, what their application is, and trying to design a thing in-house would give them the advantage of how to modify it or tweak their architecture according to the software they have. But if they want to go with a outside vendor, it would be difficult for them, especially like given the cycles or the time that you take for getting a hardware out. It becomes difficult because you have a hardware, you design it. Once it comes back, you verify it. Like what I say, for a simple chip, it takes like 6 to 9 months, or for a processor, it takes more than 2 years. Think about it. It comes back, and then you run your software on it, and then you have a lot of issues. It's not very efficient. Now you have to go back to the vendor, you have to ask them, and then get things done. So that is where you have your in where you develop a lot of things in house, and there are constant communication between the hardware and software team, and that is where most of these companies are trying to get a big hardware design teams in house. That will work for most of the companies.
Yeah, thanks, Kalai. So I should say the gist of it is, even if it is a software company, now they are moving to hardware. So hardware, it's going to rock hereafter, including the software companies.
See, when if you remember the slide that I showed you, right? When Amazon or Google, Facebook, they started, they were pure software companies. Now everyone has a big hardware team because they know that only if I have a hardware, I can control things and get a better performance. So they generally have their big hardware teams.
Yeah, that's great. So I think the purpose of this Alumni web series is solved. I think it is answered here very well, that hardware, it's going to be the future, and ECEMs have very big opportunities provided they equip themselves with what is expected from the industry. That is the key point.
That is sure. One more thing that I want to add is earlier when we were doing our graduate studies, we had very little opportunity or very little exposure to the industry. Like in the sense, only if you know someone, you can get into the industry, and you can get more details about the industry. But now, and even whatever you are learning, right? You were very much confined to what was taught in your school or taught in your college. But now it is like a open field. Now you can probably just need an internet or a good time, and then you can go and take courses from any big college, right? So any big university from MIT or UC Berkeley or anything. So you are not confined within the walls of your college or your classroom. So it is your input that is required. And second thing is um, the industry part, right? Earlier, you didn't know what was going, so you got a chip, so you didn't know what is that. Now, there's a lot of information available on the internet about how to design a chip, how to implement how is the chip implemented. Especially if you're interested, there is a website called opencourse.org. I'm not sure if people have looked at it. That gives a lot of information about how standard protocol chips are implemented, especially if anything like an AMBA bus or not an AMBA, so any of the interconnect chips are implemented. So you get an idea about what um, chip looks like, what are the different things in a chip. Uh, Especially when we were studying, we didn't have this exposure. So only thing is probably we wrote a small Verilog program or a VHDL program. That is it. We didn't know how a SOC was designed, how a physical design was done, and things like that. Now you have a lot of information available, so it's up to the student to go and take a look at it and understand how it is done. And the other thing is, now with open source and things like that, there are a lot of people in the industry who are part of these forums. They give you information that they have learned over la- over the long experience in the industry. So it also gives you a helping. It also puts you across to them, and they also probably, if they find that you are good at implementing, understanding things, it will also be easy for you to get into the industry. So it is finally, it boils down to, okay, do they have the time? Are they curious enough to know things? So If the student is really interested, then they have a lot of opportunities.
True, Kalai. The curiosity is the one which is going to drive you always, right? So we have to keep our curiosity alive all the time so that we keep learning. Nothing else is needed. Now, once you have the curiosity, you automatically start moving forward. What is it? What is it? What is it? Yeah, thanks, Kalai. And any questions from the audience? Over to MOC.
Thank you very much for clarifying our doubts, sir. No matter what language we speak, a kind and smiling thank you always speaks to everyone's heart. Now I cordially invite Mr. Harish, final year, to propose the vote of thanks.
A very good morning to one and all virtually present here. I deem it as a great honor and privilege to propose the vote of thanks on this memorable occasion. First and foremost, I would like to thank Dr. K.S. Rangasamy, MJF, Chairman, KSR Education Institutions for supporting us. I would also like to extend my thanks to Mr. R. Srinivasan, Vice Chairman, KSR Education Institutions. Next up, I would like to thank our respected Dr. K. Tyagaraja, Chief Executive Officer, KSR Education Institutions. I would also like to express my heartfelt thanks to Dr. R. Gopalakrishnan, Principal, KS Rangasamy College of Technology, for your marvelous support. I would also like to cordially thank Dr. KB Jayanti, Head of the Department, Electronics and Communication Engineering, for giving us all the support we needed to make this event a grand one. At last but not the least, I would also like to thank all the faculty members for the valuable contribution and along with all the participants who are virtually assembled here in seek of knowledge during this pandemic. Thank you.
Thank you, Harish. The student can sign off the session and all are requested to join the evening session without fail.
Hi, Kalai. Thank you. I think it's too late for you now. Are you there? Kalai?
Ma'am, he is disconnected, ma'am.
Okay, I'll talk to him. Thank you.